this next talk is going to be on cloud storage of DOE-funded DAS data for public accessibility. I think this is going to be a really big step for getting access to these massive scale data sets. So our presenters are Nicole Taverna, whose background is in geophysics and computer science, and who's a geothermal data analyst at the National Renewable Energy Lab, or NREL. And she'll also be joined by Michael Rossol, who's a data science researcher. His background is material science, and he works in a variety of energy applications. He's in the Data Analysis Tools and Applications Group, which is part of the Strategic Energy Analysis Center at NREL. Thanks very much, Nicole and Michael.
All right, thanks for that introduction. Michael and I are going to be discussing NREL's approach for storing high volume DOE-funded DAS data in the cloud for long-term public accessibility. So the Geothermal Data Repository, or the GDR, is the designated place for scientists working on geothermal research funded by the US Department of Energy to upload their data. This process includes data submission by researchers, data curation by NREL, and the data being made publicly accessible through a variety of nodes. The diagram on the right shows all of the places or nodes where GDR data may be accessed. So as you all know, DAS is extremely valuable to the advancement of multiple industries. However, these data sets are often on the order of tens of terabytes, making them too large to store and transfer efficiently using conventional means. It's also difficult to find an organization willing to cover the costs of data storage indefinitely. And while storage on hard drives is the simplest solution, typical hard drives experience a failure rate of about 1.27%, which seems insignificant, but it equates to losing more than 10 terabytes of data for every petabyte stored. On top of this, storage on hard drives reduces ease of public accessibility. And so we're going to talk about our team's chosen solution to this problem. And I'm going to pass the mic over to Michael to talk about some specific concepts and services that we're applying.
All right, thank you, Nicole. Hi, everyone. My name is Michael Rossol. I work with Nicole at NREL as a data engineer. And one of my roles is the project manager for our Open Energy Data Initiative. So this is a DOE-funded initiative to partner with Amazon Web Services to provide more seamless access to very large data by putting it in the cloud and then building cloud optimized tools around it. So this is an example of the Tomo data. It is hosted on AWS within their public datasets program or open data registry. And so we've uploaded the raw segue files. We have also we are currently in the process of converting those files into HDF5 format, which from some of the discussions I've been on, it seems like is also of interest within your community. And the main reason we're interested in HDF5 format is that we have a collaboration with the HDF5 group to use their new cloud service called the Highly Scalable Digital Service. So this is just a wrapper on HDF5 that allows you to access data formatted in H5 format seamlessly on the cloud. So this is an example of kind of all the raw data up on our public bucket, and you can access it through the OEDI, or Open Energy Data Initiative catalog, which I think Nicole will be talking about later. So what is the Open Energy Data Initiative? As I mentioned, this is a DOE-funded initiative to partner with the different cloud service providers. Currently, we are working with AWS. So we built a relationship with them to allow us to add data to their open data registry. And this is a program that they've had for over a decade now that hosts government-funded and research-derived data for free in the public sphere. So they pay for the storage costs, and they make sure that it is openly available to anyone that just registers with AWS to get an account. And there's no egress fees as long as you use it within the same region. So all of our stuff is out in Oregon and US West too. And the goal behind this project is to kind of open up the next paradigm of open data within DOE. So historically, you've had data repositories like the GDR that have worked great for small data. This, as Nicole mentioned, it becomes quite problematic when you start to have terabytes and terabytes of data, like this poor Tomo DAS data set. And so we need to have a new solution, and we think that the cloud really is that solution. And the reason for that is, one, they have these public dataset programs that provide a free way to store the data for perpetuity and make it available to the public. But more importantly, it also provides an ecosystem where you can store the data, compute on the data, and bring in different other data sets to promote innovation on those data sets. So by being able to leverage both the free cloud storage and then the state-of-the-art cloud computational resources, we're really hoping that this can push innovation. Not only are these data sets very, very hard to store and make available to the public, they also require a lot of computational resources to be able to really do analysis on them. And that's something that the cloud has a lot of at a very reasonable cost. So that's the goal of this data lake, is to bring the resources, both storage and computation of the cloud, together in one ecosystem that will hopefully enable innovation and improved analytics across different sectors, DOE, academia, industry, etc. So this is kind of our visualization of the data lake. You have all of your data resources that are feeding into the lake. And our colleague John Weirs puts it perfectly. The idea here is that we put all the data into the lake, and instead of the old GDR approach of taking your data out of the lake and taking it home with you, instead we want people to come to the lake, bring their own data, bring their resources, and camp out around our lake to do their analysis. So the idea is we want to bring everyone to the data instead of trying to give the data away to people. And we again hope that this will lead to better innovation, but we also hope that it'll lead to improved collaboration, because we're providing an entire ecosystem where multiple people from academia, industry, the national labs can all be working on the same data set in the same ecosystem, be able to share code, share computational resources, etc. So we really hope that this will be a new paradigm that will improve the ability to both access but also analyze and innovate on these large data sets. So this is what this looks like on AWS. So we have our data sets on AWS S3. This is a blob or object store. It's relatively cheap storage, but the downside is that it literally stores everything as objects. So you can't open up a Word file and edit it. You can't open up an HDF5 file and edit it on S3. It's just a physical object with all the information. And so along with the data, what we've been developing is these cloud optimized tools. So one of them I mentioned earlier is HSDS. That's the HDF group's cloud optimized solution for HDF5 format. We also have a lot of data sets that are more database format like, and we're using AWS Glue and Amazon Athena, which are managed services that allow for scalable, very scalable queries on databases or database-like structures. And then the idea here is, between the free data being stored within the public datasets program, our cloud optimized tools, we can then enable analysis within a variety of different platforms. So Tableau, MATLAB, Jupyter Notebooks, Python, etc. So most of these tools are accessible in multiple ways by multiple languages, whatever you're comfortable with. So finally, what is HSDS? So as I mentioned, this is the HDF group's kind of solution for the cloud. And how this works is we take an individual HDF5 file and we map out all of the chunks of data that are within it. You can load data into the service in two ways. One is you can take your file and break it up into millions and millions of individual objects that get stored on S3, and then the service maps the original file format to those objects and can load them into memory one at a time. Or more recently, they've been able to use some updates to AWS that allows them to map the actual location of all of those chunks of information within the file, and then just pull out the the bit ranges that correspond to the data set or piece of the data set that you're interested in, load them into memory. And so what this does is it really gives you access to whatever size of information you want, whether that's 1 megabyte, 1 gigabyte, or several terabytes. It allows you to query across those ranges of data sizes. It also is highly scalable, so it's as performant as the resources you throw at it. You can spin up a very large service that has hundreds of containers or workers, and you can access a very large amount of data or have lots of people accessing data at the same time. So currently we have a publicly available service for people to kind of get an idea of what the data looks like. I will just note that you get a lot of traffic, and so it's not really meant for scientific research. Your requests will probably crash if you request too much data, but the HDF group does have a managed service that will allow you to access our data since it's in the public sphere. And we can also, if anyone is interested in really doing some heavy analysis, we can help you through the HDF group stand up your own service that will give you dedicated access to this data in a very seamless cloud optimized manner.
Okay, so you guys have already been introduced to the Tomo DAS dataset that was collected in 2016 at Brady's Hot Springs geothermal area. And so this is the data set that NREL has had the chance to experiment with storing in S3 and providing public accessibility to via OEDI. And so this is our first success in the geothermal sphere, specifically with DAS, but we have other data sets on OEDI as well in wind and solar. So this management technique is especially useful in that it allows on-demand public accessibility, and it can eliminate the need to download the data, which is often a big time consumer. The figure on the right shows an unknown event that was observed in the Tomo DAS data, and the importance of public accessibility for the purpose of collaboration is demonstrated by this event being labeled as a mystery, because if more people had access to this data and were able to collaborate in interpretation, it may get interpreted as not a mystery event. I'd just like to note that since this paper was published, this event could have been interpreted as something other than a mystery event, but I have not read anything with updates on that. So here's a screenshot showing a portion of what the Tomo DAS GDR submission includes. You can see that there's links to the vertical and horizontal data in OEDI's S3 bucket viewer. There's also links to the S3 data as it's stored on AWS. And there's a link to the datasets documentation, as well as a link to an interactive Jupyter notebook. And there are a couple other files in the actual GDR submission, but this is mostly what's relevant to the concept we're discussing here. So now I'm going to walk through the tutorial notebook. Let me switch screens. So can you guys see this notebook? Just to be sure.
Yes.
Okay, great.
So this, if you want, though, just to get the text a little bit bigger. But...
Oh, good idea.
Perfect. Yep, that looks great.
So this is an abbreviated form of the full notebook that we have hosted in GDR submission 980. This notebook is not currently in the GitHub repository that all the other tutorial notebooks are stored in, but we can talk about adding it if that's of interest. So the full tutorial notebook for the seg-wide data is listed in GDR submission 980 if you're interested in accessing it. So prior to running the script, you want to make sure you have a few modules installed in your environment, such as NumPy, Matplotlib, sys, os, photo3. And based off your desired format, you'll also need to install the following. So if you're interested in the SegWi format, you'll want ObsPy and AWS CLI. And if you're interested in the HDF5 format, you want S3FS and H5Pi. And if you're interested in accessing the data via HSDS, you'll want H5Pi-D, although since the HSDS method isn't fully built out yet, we ask you to hold off on attempting to run that method just because it doesn't work yet. And so if you're using AWS CLI, be sure to configure it within the terminal or command line with your AWS login credentials using AWS configure. If using HSDS, you'll also need to do some configuration within the terminal, which we'll talk about when we get to that section. So this first block just imports the modules of interest and sets up the logger, and the resource is set to S3 because that's where the data is stored. You also specify the bucket, which in this case is NREL-PDS-Porotomo, and we'll set the current working directory. So if you want to count the total number of objects in the Porotomo S3 bucket, you can loop through each object using bucket.objects.all. And so the output is listed here. You can see there's over 63,500 individual files as well as directories, because those are counted as objects as well. In terms of accessing the data, there's a few different ways that you can do so. The first is reading the data directly from S3, which you can do by specifying keys, which is what AWS uses to identify specific file objects. And so here's two that we'll read in. And then if you're interested in downloading the data, you'll want to specify some file names as well, because you'll need to store it somewhere, and then you'll need to read it back in using those same file names. So for reading in the data directly without downloading, you can use this datastream.append. And the data stream is just an array. Sorry, you don't use datastream.append, you use obfpi.read. And you can append the file objects to an array, which is called datastream. And so obfpi.read takes in the URL of the location of the data, and the format is seg-y. And so here's the output. You can see that there's between 8,721 and 8,719 traces per file. Oh, I'm interpreting this wrong. There's 8,719 traces per file in the two files that we're looking at. And it shows the time associated with that, and the frequency and the number of samples. If you want to read in all files, you can, but it's not really recommended because it will take a really long time to run, and you can just pull in the individual files from S3 as needed using the method above. So I'm not going to talk about that in too much depth. If you want to download the files and then maybe later read in the data, initially you'll want to make sure you have a directory structure set up. And so that's what all this is here. It's just creating some directories to store your data in to make sure that it's in a location that the script can pull it from later on. And then for actually downloading the files, you can use this bucket.download_file with the key passed in as well as the file path. And so we loop through each index in the array of keys so that we can access both the file name and the key to store the data at those specified file names. And again, you can download all of the files, but it's about 40 terabytes of data. And so most normal computers don't have that kind of storage, and it'll also take a really long time. So I'm not going to spend too much time on this either, but it's a similar method to what's talked about above. You're just looping through all of the objects in the bucket. So if you're interested in the HDF5 files, you can use S3FS and H5Pi to access them. We'll want to specify new keys because the H5 files are in different directories than the seg-y files. And so this is pretty much the only thing that changes in the key. So again, looping through all the keys, we're going to set the path to a different format of the URL of each file with the key appended. And then you can use s3.open using the specified path and h5pi.file to access that file path, access the file from that file path. And then again, you can append each file to an array called data stream if you wish. And this is what the output looks like. So you have the channel, the CRS. I'm not sure what DAS is, but you also have time and trace, and then X, Y, and Z. Those are stored in array, well, HDF5 type objects. And then this is HSDS, which is what Michael talked about, is coming soon. And so to use this, you'll want to install h5pid. You want to configure HSDS using hsconfigure, and then enter this information at the prompt. And so this is what Michael was talking about, how this API key is rate limited, and you might end up with the file or the notebook crashing if you try to use this key for too large of files. And so if you want to visit, or if you want to get your own API key, you can visit this link here. And you can also add all the above contents to a configuration file if you'd like. And so for this method, again, you loop through all the keys and set a path, and you use h5pid.file instead of h5pi.file to store the file as an object. And then you can append them again to an array called data stream if you'd like. And that is all I have.
Thanks. This is really interesting. So I think we've got time for a quick 1 or 2 questions. I saw there were some Q&A in the text chat box, but I think all of those got answered. If there are any more questions, go ahead and type those in. I'll read them out loud for you all. So I've got a quick one while there aren't any others. So I was curious about the Amazon Athena tool. I haven't used that before. And you mentioned it was like for database browsing.
Yeah, so
surrounding the files, or is that actually the files themselves?
yeah, so Amazon Athena is pretty cool. It's a serverless database format, and so what it does is, let's say, for example, you have a whole bunch of CSV files in a bucket. You can use what they call crawlers. So they're just kind of these machine learning bots that they send over the bucket, and it determines what is in each of the files and creates a serverless kind of database image of that entire bucket. And then you can run SQL-like queries against Athena, and it will go pull out that subset of the data from this massive repository that you have on the bucket. So it's kind of their solution to, you don't have to stand up a whole database, you can just add data to the bucket and it'll kind of refresh itself on whatever schedule you want.
Awesome, thanks. That's actually something I just ran into recently and wasn't sure how to deal with, so thank you.
You're welcome.
Yeah. I guess there's also a question from Wangping Chen about whether there's communication between IRIS and DOE on this topic. IRIS has made some moves towards cloud systems recently, and around the same time as DOE doing this. Are you all collaborating at all?
Not that I know of. Nicole, do you know of anything?
Yeah, so last fall, it could have been winter, but at the DAS workshop at AGU, I had some discussions with some of the IRIS folks. And it seems like we're taking similar approaches, but there hasn't been much collaboration, if I'm being honest. We're in contact, but yeah.
Yeah, well, there's lots of room as both of these services are kind of growing, and really cool. Thank you both so much. With our last few minutes, I think Nate Lindsey is going to cover signing up for lightning talks. And kind of next steps for our call on Monday. So thanks very much, Nicole and Michael. This was really cool to hear about.
Thank you for having us.
Yeah, thank you so much for the invite.
Okay, so I think that was great. I'm just going to present two quick slides. So the format for Monday, day 3, is going to be something like this. So we're going to have lightning talks by workshop participants, by anyone who wants to present something about their research in DAS, or maybe something they found in these notebooks today. Between now, you have 5 days between now and then to interact on Slack or kind of continue exploring these notebooks. So if you have, it's just 2 minutes and 1 to 3 slides. So if you're interested for the, just want to make sure I'm not on. Yep, okay. So yeah, 1 to 3 slides. You can send that to this email here. You can fill out this Google form, so we kind of register you, and this is just going to say, like, what is your email, and then send your slides, your actual slides, so we can compile one continuous reel to this email here. And please do that by Saturday in 3 p.m. Eastern, so that we have enough time to kind of post the order so everyone knows before Monday, day 3. So the talks are limited to 2 minutes. So please, keep it brief, and anyone who wants to is welcome to present. So students, postdocs, professors, professional people, anyone who wants to present, please take a minute to do that. The second part of day 3 is going to be really these in-depth or advanced DAS talks by Ariel Lelouch, Vera Rodriguez-Tribaldos, we have Julia Correa, and then Alexei Titov. So you can see that these different topics are each going to talk about very different ways to work with DAS dataset, from earthquake analysis, what you can actually do with this earthquake wave field in terms of beam forming or velocity analysis in the well. We can look at really long period response and static deformation. You can do advanced imaging, migration, and this kind of thing for CO2 sequestration monitoring, and also flow loop monitoring or laboratory studies to understand more about what the DAS is actually recording. So stay tuned for this, and we look forward to seeing you on Monday on day 3.